Hello, my name is Uzi Per, and in this talk I'll present my work on quantum relay channels. So I'll begin with a bit of motivation. Relaying plays a crucial role in enabling long-range communication, for example, in optical communication in free space. There are different phenomena such as absorption, scattering, and turbulence that limit the distance. And by dividing the communication link into segments and placing a relay terminal between them, we can rectify problems such as photon loss and operation defects. Therefore, relaying is a promising solution for long-range communication. And here we consider this three-node network, where between the sender and the destination, we have this relay node that assists the transmission from the sender to the destination. Now, in a multi-hop network, synchronization is essential. Let's suppose the operation is governed by a central clock that ticks n times. Now, here F represents the encoder, which transmits an input AI at time I. Okay, so between the ticks I minus 1 and I, the sender and the relay transmit the inputs AI and DI respectively. Then at the clock tick I, the relay and the destination receivers receive the outputs EI and BI. This implies strict causality. Here the relay prepares the state of DI while having access to the past relay outputs, E up to time I minus 1. The classical model was introduced by van der Meulen in the 70s, and since then there has been a long history of contributions in the classical literature on relay channels. As for the quantum setting, there have been works on the classical quantum relay channel, where we assume that the inputs AI and DI are classical. Okay, so Savov et al., Boche et al., Ding et al., they all considered classical quantum relay channels in different settings, and they derived the code forward bound. They considered bidirectional relay, multi-hop bounds. And another setting that is somewhat related is environmental systems. Now, in this work, we consider the transmission of messages via a fully quantum relay channel. And we establish three bounds that are based on different coding strategies. Similar to the approach in the classical case, the capacity of the classical relay channel is an open problem, but we have useful bounds. So here I developed bounds using three strategies. In the partial decode forward strategy, the relay decodes part of the information and sends the information to the decoder. In the measure forward strategy, the relay doesn't decode any information. Instead, it performs a sequence of measurements and then sends a compressed representation to the receiver. And in the assist forward coding strategy, we use the transmission to the relay in order to generate entanglement between the relay and Bob. And then the relay can send information to Bob using rate limited entanglement assistance. We will also consider an example of a depolarizing relay channel. We will see that without the relay's help, the capacity is 0. However, using the relay, we can achieve higher rates. Okay, so first I'd like to introduce the notation. Here we have a quantum relay channel. This is a map that has two inputs, A and D, and two outputs, B and E. And we can see in this figure that A belongs to Alice, to the sender, B belongs to the destination receiver, and the systems E and D both belong to the relay. Okay, specifically, A represents the sender's transmitter, D represents the relay's transmitter, so D is the relay input to the channel, B is the destination receiver, and E represents the relay's receiver. Okay, so E is the output of the channel that goes to the relay. Now, I'd like to point out that the relay is only required to assist the transmission of information, and in some coding strategies, the relay doesn't decode information at all. We will see this in the measure forward coding strategy. We will also consider special cases. Specifically, we define a degraded channel such that we have this degrading channel from the relay output E to the joint output of the destination receiver and the relay output. Intuitively, this means that Bob's output is noisier, which is typically Bob's output is noisier since Bob is usually further away from the sender. We will also be interested in a Hadamard relay channel, which is a degraded relay channel such that the relay receives a classical observation. So instead of the quantum system E, we have a classical variable y1. However, the other systems, the inputs A and D, and Bob's output B, they are all quantum. So here we define a code for the relay channel. As usual, we have a message set and a coding map that prepares the input state. However, here we have a sequence of strictly causal relay encoding maps. Strictly causal means that the relay has access to the output systems up to time I-1. And using this access, the relay encodes the state of the input di at time I. Now, in the quantum case, where we have quantum inputs and outputs, the definition is a bit more complicated as we need to account for the post-operation. For example, if the relay performs a measurement and sends a classical outcome di, then this encoding map is a quantum instrument where the system E bar represents the post-measurement system. As we know, in quantum measurements, the state can change as a result of the measurement. So if we perform a sequence of measurement, the state can change many, many times. Okay, so as usual, the Bob decodes using measurement. Now, we say that the rate is achievable if we can encode such that the error probability tends to 0, and the capacity is defined as usual as the best achievable rate. So now I will present several bounds. I will begin with a bound that is based on the decode forward strategy, or to be more specific, a partial decode forward strategy. In the partial decode forward strategy, the relay decodes part of the information. So here we have the following formula. We have a minimum between two information measures. The first is the Holevo information to Bob, and the second information measure is a sum of two mutual informations. The first goes to the output of the relay, and the second corresponds to Bob. And after we've taken this minimum, then we also have a maximum over an ensemble of product input states. Here we have an input state for Alice, for Alice's transmission, and we also have an input state for the relay transmission. Now, in this formula, we have three auxiliary variables. The auxiliary variables x0 and x1 select the input states, but we also have this auxiliary variable u. So what does u represent? If we take u to be null, then we get direct transmission. We get the Holevo information as a lower bound. On the other hand, if we take u to be equal to x0, which selects the input state, then we have a full decode forward bound that can be achieved by requiring the relay to decode the entire information. So we see that this auxiliary variable u represents the amount of information, the information that we require the relay to decode. So our third result is that the partial decode forward bound is a lower bound. The proof is based on a block Markov coding scheme. In this scheme, we have a sequence of blocks. Each one is of size n. And in block J, in block number J, the relay decodes a message component from block J-1, but not the entire information. Some of the information is only decoded through the direct link without the relay's help. This generalizes a previous result by Sabor et al., who considered classical quantum relay channels, while here we consider a fully quantum relay channel. We also consider the special case of a Hadamard relay channel, where the inputs are quantum, both output is also quantum, but the relay receives a classical observation Y1, and then we have a single letter capacity formula. Okay, so the next bound that I'd like to present is the measure forward bound. The formula is a bit involved, so I will skip the details and just give the intuition. Here the encoder and the relay prepare input states of A and D, respectively. The relay receives E and performs a measurement. The measurement yields an outcome that we denote by Y1. Then the measurement outcome is compressed and encoded by the relay as Z1. Now, we interpret this term n times the mutual information between the compressed representation Z1 and the measurement outcome Y1 as the number of information bits that are obtained from the compression operation, while n times the Holevo information to Bob is the number of information bits that the relay can send. And this limitation is reflected through the maximization constraint, where we have the compression rate is bounded by the transmission rate from the relay to Bob. Okay. Now, the previous coding schemes that I presented, the partial decode forward and measure forward, they can be viewed as a quantum analog of classical coding approaches. On the other hand, the next coding strategy is based on a novel approach. Here, Alice simultaneously sends the message to the relay, and she also generates entanglement assistance between the relay and Bob. Subsequently, the relay communicates the message to Bob using a rate-limited entanglement assistance. So here we consider a quantum relay channel with orthogonal receiver components, where Bob's output has two components, B1 and B2. And the channel also has a product form. This is why we say that the outputs B1 and B2 are orthogonal. So here, Alice can send a message to the relay, provided that the information is bound, that the information rate is bounded by this forever information to the relay output E. She also generates entanglement. She can do this provide at a rate that is bounded by those coherent information to the destination receiver component B1 and to the relay output E. And then in the subsequent block, the relay and Bob can perform an entanglement-assisted communication protocol. This requires the rate R to be bounded by both this quantum mutual information and also by the sum of this mutual information, the coherent information, and the entanglement rate. Okay. Those bounds are based on Shor's result on rate-limited entanglement assistance. So this yields the bound that we have here, and we call this the assist forward lower bound. Now, I'd like to give a trivial example where the assist forward coding strategy is optimal and achieves the capacity. So here, in this trivial example, we have noiseless links that are orthogonal. This link from the sender to the relay can send 3 qubits. From the relay to Bob, we have 1 qubit. And from the sender to the destination, we can also send 1 qubit directly without the relay's help. Now, using the assist forward approach, Alice can generate an EPR pair between the relay and the destination, and then the relay can communicate 2 bits over 1 qubit transmission using the superdense coding protocol. So this achieves the capacity of 2 classical bits per transmission. However, the assist forward strategy is completely unnecessary. There's a much simpler approach where you can simply send 1 bit of information directly to the destination receiver and 1 bit of information through the relay using the partial decode forward. So both partial decode forward and assist forward strategies are optimal in this trivial example. Let's consider a more interesting example. This is a qubit relay channel, a depolarizing relay channel, where Bob's output has 2 components, P1 and P2. And if we look at this channel, to the output component B1 and to the relay output E, we can see that the marginals to B1 and E are completely depolarizing channels. For any input, we have the maximally mixed output, the maximally mixed state as the output. Therefore, the capacity without the relay's help is 0 in this case. However, based on the measure forward bound, we show that we can achieve a positive rate using the relay's help. So I'd like to summarize. Here we consider, we are the first to consider a fully quantum relay channel of this form with strictly causal encoding the relay. We use different coding strategies. specifically the partial decode forward coding strategy, measure forward, and assist forward. Using those lower band, we also develop a single letter capacity formula for the Hadamard relay channel. As in the classical model, we obtain the capacity formula for a physically degraded channel. This in the classical case, the quantum case, this means that the Choi operator forms a quantum Markov chain, and this is a very strong requirement. It's much stronger than the degradedness criterion that we have for broadcast channels, for example. We also demonstrated our results using the example of a depolarizing relay channel. We've seen that without the relays help, the capacity is 0. However, the measure forward strategy yields a positive rate. We are currently working on different directions of quantum repeaters, transmission of quantum information, continuous variables, and there are also other directions that could be considered, such as a T-node relay network. Thank you.